Imagine you are managing a massive warehouse where trucks arrive constantly to pick up and drop off goods. Every single truck represents a piece of data your software needs to process. The warehouse manager is the memory allocator. If the manager is slow, if they make mistakes, or if they get confused about where items are stored, the entire operation slows down. This is what happens inside your computer every time a program asks for memory. For decades, the standard manager was the GNU C Library Malloc. It is the default choice for almost every application on Linux systems. It works well enough for most things, but when you push it to the limits, it starts to show its cracks. Here is the thing about high-performance computing. You can have the fastest processor in the world, but if the memory system cannot keep up, the processor sits idle waiting. This is especially true in machine learning inference pipelines. These systems need to process requests in real time. They cannot afford to pause. When a request arrives, the system must allocate memory, use it, and then release it, all within milliseconds. If the memory manager hesitates, the user feels it as lag. This hesitation is known as latency jitter. It is the enemy of real-time performance. Now consider this. For a long time, the industry tried to fix this with a tool called tcmalloc. It stands for Thread Caching Malloc. It was designed to speed things up by giving threads their own private pools of memory. This reduced the need for threads to argue with each other for access. It was a significant improvement over the standard library allocator. However, even tcmalloc has limits. It struggles with specific patterns of memory usage where fragmentation becomes a problem. Fragmentation is when memory becomes scattered across the system like puzzle pieces that do not fit together. This forces the system to search harder for space, which increases the time it takes to allocate. This brings us to the renewed focus on jemalloc. This is a memory allocator that has been around for a while, but the recent strategic shift indicates a deeper integration into large-scale systems. Meta has signaled a pivot towards relying more heavily on this specific tool for their infrastructure. Why now? Because the scale of modern machine learning workloads has hit a ceiling where standard solutions are no longer sufficient. The renewed commitment suggests that Meta is moving from relying on external or generic allocators to a deeply integrated solution optimized for their specific workload patterns. This is not just about making things faster, it is about stability. Think about a machine learning model serving images or text. When thousands of users request a response at the same time, the system must handle thousands of memory allocations per second. If the allocator introduces even a small amount of variance in how long it takes to grab that memory, the latency jitter spikes. This causes the response times to become unpredictable. Some users get a fast answer, others wait. In a high concurrency environment, consistency is more valuable than raw speed. jemalloc is designed to minimize this variance. It manages memory in a way that reduces the need for locks, which are essentially traffic lights that force threads to wait for each other. By reducing lock contention, the system can handle more requests without stalling. The benchmarking data surrounding this shift highlights a critical distinction. When you compare jemalloc against the standard Glibc malloc and tcmalloc in high concurrency scenarios, the difference often comes down to how the allocator handles cache pollution. Every time a processor accesses memory, it checks its cache. If the allocator scatters data in a way that forces the cache to reload constantly, performance drops. jemalloc organizes memory to keep related data closer together, which keeps the cache hot. This is a subtle optimization, but in a system processing billions of requests, it adds up to significant throughput gains. However, this comes with a cost. Engineering complexity increases. Moving away from the standard library means you are taking on more responsibility for how your software manages its own resources. You have to tune the allocator to match your specific workload. What works for a database might not work for a web server. Meta is investing heavily in this because they have the engineering capacity to maintain these custom solutions. For smaller organizations, the standard allocator is still the practical choice. But for massive-scale distributed systems, the one-size-fits-all approach is no longer sufficient. There is a broader implication here for the industry. As systems become more distributed and more concurrent, the foundational layers of infrastructure must evolve. The renewed focus on jemalloc indicates that existing memory allocation bottlenecks have become critical performance constraints. Companies are realizing that higher-level application tweaks are not enough. You need to fix the foundational infrastructure. This trend suggests that future open-source standards will likely be driven by the internal optimizations of large tech companies. Concepts like formal verification, which ensure the code is mathematically proven to be correct, are becoming relevant here. Security and correctness are as important as speed when you are managing memory at this scale. Consider the future of distributed systems. If you are building a platform that handles sensitive data or requires strict security guarantees, the memory allocator plays a role in preventing vulnerabilities. Memory corruption is a common source of security flaws. By using a more robust allocator like jemalloc, systems can reduce the attack surface. This aligns with the industry trend where high-performance systems prioritize fine-grained control over memory fragmentation and latency. It is a trade-off between simplicity and control. You give up the ease of the default library to gain the precision needed for scale. The takeaway for anyone building large-scale applications is clear. If you are dealing with massive-scale multi-threaded applications, you cannot rely on the standard library allocator to maintain throughput. You must consider custom or heavily tuned allocators. This is essential for maintaining performance and reducing garbage collection pauses. The decision to invest in tools like jemalloc reflects a recognition that memory management is no longer a background task. It is a core component of system performance. As we move forward, we will likely see more systems adopting this level of scrutiny. The goal is to eliminate the jitter, to ensure that every request is handled with the same speed and efficiency as the last. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.